we're just starting our second session here. I will end the poll. We had a good 93% participation, and I'm going to share the results. So as could be expected, you can see I am a researcher is a big return. I'm a researcher, and soil moisture is a secondary research topic for me, is actually the most, not a primary source. So there's a lot more people interested in soil moisture than actually doing the research. We wind up feeding lots of other data sources. A few practitioners, data providers, and then the mystery folks. I'm none of these, but still interested in soil moisture. As well, what is our component here? We have 45% federal government. Nice to see there's lots of representation by federals. Also, this is free. And that's one thing that federal government employees like, is something free and less paperwork to do than some state governments and universities, as well as non and for-profits. So we're always trying to increase our base. I put a link in the chat, and I'll add more later, connecting to the National Coordinated Soil Moisture Monitoring Network email list. That's where we do lots of our advertising for events like this, as well as our network operator workshops and end user listening sessions. So that is one way that we keep track of who gets what emails, and not too many emails, to be sure. And that's our primary means of communication for this conference now. So I will also add some questions have been asked about the recording sessions. We are recording everything. We'll chop them up into pieces. Each session gets its own video, and you can watch these all online later. You can watch them at 1.5 speed if you want to see people talk like chipmunks, and you get done faster. So it's efficiency as well. I'll also repost. There's a Jamboard where people can post their interests and comments on various soil moisture aspects. And we'll put that in the chat so it's fresh in the list. You can see Marina put the network listserv up there as well. And also to mention that we're going to have a survey at the end of the workshop, so we can find out what worked and what didn't work for you from these sessions that we present. We're always trying different things to see what is useful for you. And we want to try and optimize as we go forward, and we'll have a poll question later. What type of conferences or workshops will we be attending in the future, and what's the best way to make that beneficial for everyone involved, if you're in person or via telephony. So we're hoping to make all of our future conferences hybrid, at least, and we want to make sure that we have good engagement and it's beneficial. If you're going to spend your time with us, we want to make sure not to waste it. In that vein, we're going to move on to our next presentation, and the next three are on sensor networks, and these are recorded presentations. So we have, for the first speaker, Ron Leeper is in the, should I do the right person? Is in the chat room, and we'll be able to answer questions. And just type them in the chat and he'll be able to respond because he's already recorded. So let me share the presentation and make sure it works.
All right, thank you so much for the opportunity to come and communicate with you all today about some of the exciting stuff CRN's got going on with our new clima sensors in terms of research and applications. My name is Ronald Leeper. I'm with the Cooperative Institute for Satellite Earth System Studies, and we have a lot to unpack here, and I apologize for the whiplash we're going to experience halfway through as we transition from a sensor comparison study to a machine learning. So if you didn't already know, the USCRN is transitioning to a new clima sensor. We began this transition in 2017. And as with everything involving COVID, it got slowed down quite a bit. But during this slowdown, we've had an opportunity to have several years of data where we have both hydra and Acclima sensors at the same location. This map is showing you where we have Acclima sensors installed in green. And I should say that this doesn't necessarily mean they're all Acclimas, but it's a mixture of hydra and Acclima. So there's at least one Acclima at these stations at one of our depths among one of the redundant sensor types. We also had an opportunity when we introduced the new Acclima sensor to revamp our QC approach, and this was done in such a way that allows us to pursue machine learning opportunities as a QC strategy. So we'll get into that and unpack that. So first thing we're going to talk about is the in-field comparison among all those stations that we have at least one Acclima sensor in. And to understand the layout of this graph here, what we mean by mixed sensors, the goal of this analysis was primarily focused on understanding what happens when we mix Acclimas and hydras together and produce a layer average. We want to know, how does that layer average change? Right now, even though we've had Acclima sensors in the ground since 2017, we don't have those data available in CRN's front-facing products. And eventually, when we turn those on, the layer averages are going to adjust a little bit. And here we want to know, what sort of adjustments are we talking about? How large are they? Are they significant? So the y-axis is a mixed sensor. This is a mixture of Acclima and hydras combined into that layer average. And the hydras only layer is what we have currently. It's essentially, of the hydra only sensors, what does that layer average look like? And in this scatter plot, you can see that the overall agreement is really, really well. We see some variations, small variations on the drier end of the hydra only observation. Between 0 and 0.1, there may be a slight wet bias when we start to introduce Acclimas. On the very wet side of the hydra range, 0.5 and above, particularly above 0.6, we do see a drying, or they're below the 1-to-1 line, indicating that the mixed sensors are reporting slightly drier layer averages. To understand that a little bit more, I got these graphs here of mean differences in RMSE. Really focus on the y-axis here of the mean difference. This is mixed layer average minus the hydra only. These are in thousands of volumetric, and really the differences are essentially 0 across all the depths. There is some slightly drier values at 5 centimeter, wetter values at 20 centimeter. When we do the RMSE on the right, you actually see the biases, or the size of the root mean squared error is roughly the same from 5 all the way down to 50 centimeters. There's an interesting thing going on with the 100 centimeter level that we're still trying to unpack, and we believe it may be associated with some issues with the particular Acclima sensor we have at that depth. So we're still trying to understand that a little further. When we break the differences down by soil type, this is really where we begin to see the difference in the Acclima and the hydra sensors. Not so much in sand or silt, but really with clay. And again, these are layer averages. So when we talk about the 3 stations here, that's in the parentheses there, we're mixing Acclimas and hydra. So the actual difference between Acclima and hydra for clay soils is much larger than what's shown in these graphs. But we're seeing mean differences in one direction. We're seeing the differences in one direction, so you see negative values. So when we mix in the Acclima, we're getting drier observations for these clay stations. It's much more pronounced at RMSE space, somewhere between the mean being somewhere between 0.08 and 0.1 root mean squared error. Turning our attention a little bit to soil temperature. I know this is a soil moisture network, but our sensors also report soil temperature, and this is a piece of that sensor. These results are a little bit surprising to me. There is a diurnal difference between the Acclima and between the mixed and the hydra only. When we incorporate Acclimas, we get much warmer daytime 5 centimeter level data and a slightly cooler evening hour temperature data. This diurnal signal reduces with depth and is pretty much negligible at 50 and 100. We're actually in talks with Acclima to understand these differences, and we're probably going to be doing some sort of kind of lab experiments to understand which of these sensors is closest to actual temperature. And it may be due to installation, and these biases may change over time. These are all the different things we're trying to understand. So overall, to summarize our in-field comparisons, we found that the two Acclima, the Acclima and the Hydra sensors compare really well across most soil types except clay. And because we see it for one soil type, we believe it has to do with our equation where we're converting the dielectric to volumetric. Our assumption of silt loam may not hold true for these clay content soils. This graph here I'm showing you is at our Selma, Alabama. This is a clay station. And the black line is showing you our current calibration, our current conversion. And the red line is one adjusted for the soil properties at that station. And you see when you get those really wet Hydra values, that's reduced when we update that equation. And so it's moving toward what we're seeing with the Acclima sensor. So that's a good sign, some promising results there. We may be able to correct this historically. As far as the temperature analysis, we kind of want to know which sensor is more accurate, giving us a better measure. And then we want to know, do the differences diminish in time? And this may be, you know, grass becoming more thick and it shields the sensor maybe from direct sunlight or direct soil insulation of the soil. So we're still trying to understand the differences between those two sensors. All right, so this is the point where we're going to transition really quickly and talk about another study incorporating machine learning as a QC strategy. So I mentioned earlier when we introduced the Acclima sensors, we actually got to think a little bit more about how we want to QC the Acclima sensors, maybe a little bit differently than the Hydras. And the approach we took was to be very specific and identify individual hours and relate them to a particular QC tag I have shown here on this table. These tags aren't set in stone, so we can introduce new ones as we see new issues arise. But these are the general ones that we found during the QC process from 2017 to currently. And when it comes to machine learning, it's good to have a good training data set. And we took this approach. It requires a little more effort on the front end, but now we can actually train a learning algorithm to say, hey, this is what a spike looks like. This is what noise or a drop to zero or too high. These are what these different types of errors we're seeing in the data looks like. So when we apply machine learning, we can not only ask, hey, how well is the algorithm detecting bad data versus a non-flag data, but is it able to tell us why it's flagged? Is it spike, or is it noise, or is it something else? So these are some of the things we wanted to explore in this first pass of applying machine learning. So here's some overall results. If you're a machine learning buff, you might know some of these. We use a random forest and an XGBoost method. These are basically tree type learning operators, and they were trained on all of our sensors from all 5 depths in addition to temperature and precipitation. So all that information was given to the machine learning algorithm so it can find relationships between those and predict good data from bad data. Our results here are on the right. That top bar or that top plot is showing you that 97.7% of all the manually identified non-flag data was correctly identified as non-flagged by the algorithm. Very rarely was good data identified as a spike at 0.04% or noise at 0.13%. If we come down to the middle plot, we're showing you that 88.4% of all the manually identified spikes were captured by our learning algorithms, and almost never did it ever mix up a spike or a noise, but when it did mess up, it reported a spike as good data, so about 11.4% there. If we come down to noise, it did a little bit better with noise at 92.2% of identifying those. And again, it never really mixed up noise and spikes. If it missed it, it actually reported as good data at 7.4%. So overall, if this is our first pass at using machine learning, it did a really good job. One of the challenges we have is that random forest and XGBoost, these methods really require a snapshot in time as opposed to a time series, and therefore it makes it very difficult to operationalize. And so our next steps are to actually apply recurrent neural networks. This is a type of machine learning operator where you can feed in time series information, and we believe this will really improve the detection of spikes. And so we're really looking forward to that. So our next steps, basically we believe we can integrate the Acclima and the Hydra sensors together. Their overall performance was very, very similar, except for those few stations that we have clay content soils. And our goal there is to recalculate our historical hydro data using soil properties at our individual stations. So more to come on that. But this is important because when we transition to the Acclima, we really, really want to ensure that our standardized soil moisture product that we just recently released, Mike's going to talk a little bit more about that in the next 30 or 40 minutes. We want to make sure that isn't impacted. And again, this is important for hydrological studies. This graph here is showing you some analysis from a paper that was just recently published looking at our anomalies. This graph is showing the distribution of our anomalies from all 5 depths and then top and column layer aggregates prior to drought onset from a 1, 2, 4, and 6 week perspective. And so it's really important that we correct the hydras as much as possible, and therefore we preserve our standardized measures so we can do these hydrological studies in the future. On the machine learning side, we're really excited about an opportunity provided to us through the NOAA Hackathon. We just got access to NVIDIA and their machine learning experts, and we're going to try to take what we've already done and redo it using recurrent neural networks, RNNs, to operate on time series, and this will really allow us to find ways to integrate machine learning practices into our QC approach. So looking forward to that and a lot more to come. So thank you for listening, and I'm looking forward to discussion to come.
Thank you, Ronnie. And Ronnie is in the chat answering a few questions. And if we have any live questions, we can take 1 or 2 right now. And if not, I'm going to take the opportunity to move forward. I do know Ronnie was responding to folks. I'm dealing with one little issue here that I will try and resolve in the near term. So let me go on to the next speaker, who is Dr. Tyson Ochsner, one of our co-organizers, and Oklahoma State University, who will be presenting on a slightly different topic. Make sure I have the right.
Hello, my name is Tyson Ochsner, and I'm happy to have this opportunity to share with you some of the things we've been learning about how soil moisture measurements can improve grassland productivity estimates. We have a great team for this work that I want to acknowledge and thank, especially Dr. Eric Kruger, who led this effort. And we're also very grateful for support from our sponsors and data providers, which are listed here on the slide. The motivating question for this research is to understand how can increasingly available soil moisture data be used to better manage our grasslands. These are grasslands which are often threatened by drought, by overgrazing, and by wildfire. It's been a journey of discovery over the years, and so far we have learned that soil moisture conditions strongly affect the size of our wildfires that occur during the growing season in the southern Great Plains. We've also learned that the relationships between soil moisture and wildfire are different for the growing season versus the dormant season. Furthermore, we learned that direct measurements of soil moisture provide better wildfire danger warning than does the Keach-Byram Drought Index, which is widely used in the wildfire community. More recently, we've discovered the links between soil moisture conditions and the vegetation moisture content, or what they call the fuel moisture content in the wildfire danger rating systems. Today, I want to talk with you about the latest step in this journey, which is what we've learned about how soil moisture information can improve our ability to predict the productivity of these grasslands. So we had a field site here in Oklahoma where we worked to develop and calibrate the model. And the field site included 3 different pastures, like the one shown here in the photo. And I show this one because this is the site of the Marina, Oklahoma in situ sensor test bed that some of you are familiar with. The vegetation at these sites is typically tall grass prairie vegetation. The soils are very heterogeneous across these sites. There's a subhumid climate in this region, and we have observations of soil moisture at these sites. We have eddy covariance tower, and we've been out in the field collecting measurements of the grassland productivity throughout the season. After calibrating our model for those sites, we then applied it across the entire state of Oklahoma in a validation effort. And in that context, we have a wide range in annual precipitation. We have soil moisture data coming from the Oklahoma Mesonet, as shown here on the map. We have meteorological data from the Mesonet as well. Then we obtained county level hay yield information from the USDA National Agricultural Statistics Service to compare with our model predictions. So we predicted the grassland productivity at the county level across the state, both with and without assimilation of soil moisture data. And then we compared those to the county level hay yields. So I want to unpack this model for you a little bit. We used the FAO dual crop coefficient method to simulate evapotranspiration from these grasslands. And so that's represented by the equation you see here on the right. It's essentially a way of scaling the reference ET. So weather data comes in and allows us to estimate the reference ET, which is shown here. And then we use information about the vegetation in these grasslands to define these dynamic vegetation parameters represented by KCB here in the equation. And with that, we get an estimate of the evapotranspiration from that vegetation. The ET estimate then feeds into a simulated water balance, which allows us to calculate a water stress coefficient and an evaporation coefficient as shown here in the equation. Once we've simulated the evapotranspiration, then we can take this left-hand side of it, and this provides us an estimate of the transpiration by that vegetation. Once we have estimated the transpiration, we can accumulate that transpiration throughout the growing season and scale it by the reference ET, multiply it by a water productivity, that's what WP means, and arrive at an estimate of the biomass or the productivity of this grassland. So we use calibration and validation data from the moist site where we had a flux tower measuring the evapotranspiration, and we had regular vegetation sampling to determine the biomass changes over time. With that, we were able to estimate the vegetation parameters that we need for the ET model, as well as the water productivity, which should be approximately a constant for a given species. We did these simulations both with and without direct insertion of soil moisture data. So if we have measured soil moisture values, we can replace the simulated water balance and directly insert the soil moisture to get the crop water stress coefficient and the evaporation coefficient. We then test this approach again across the state, the 25 largest hay producing counties in the state, and 3 years each, so 75 site years of data for validation. To calibrate and validate the ET portion of the model, we use the flux tower data as shown here. So on the x-axis, we have time. This is 5 years worth of data. And the black line is the modeled ET with the insertion of the soil moisture data. The green line is the measured ET from the flux tower with all necessary corrections having been applied. The dashed line here are the data from the phenocam, which shows basically the greenness of the vegetation. What you can see is that we have, during the first 3 years, which served as our calibration period, quite good predictions of the model without insertion of soil moisture, shown here as FAW, fraction of available water capacity, but even better predictions of ET if we insert the observed soil moisture data. We used the last 2 years for our validation period, and we've achieved good results both with and without direct insertion of FAW. The next piece then was to estimate that water productivity, and we did that by plotting the cumulative biomass for those sites, which are the black dots here, versus the cumulative normalized transpiration. And when you do that, you get a water productivity of 45 kilograms per hectare. We don't have any good studies to compare this to in the terms of benchmarks or other data sets. So we certainly need some more research to explore how well this water productivity works for other environments. But at least it seems to reflect the seasonal dynamics of above ground biomass accumulation relatively well at this site. So now the model's been calibrated for these sites near Stillwater, Oklahoma, and then we just apply it across the entire state, both with and without insertion of the soil moisture data. And here I'm showing you the results with soil moisture data insertion. You can see that the model effectively predicted the hay yield with a Nash-Sutcliffe efficiency of 0.55 and a mean absolute error of 321 kilograms per hectare. Now, we might like that to be a little better, and maybe we can improve the model in the future, but it's certainly significantly better than if we don't include soil moisture data. In that case, the Nash-Sutcliffe efficiency was only 0.10, and the mean absolute error of 475 kilograms per hectare. Now, just one aside or one caveat in the interest of full disclosure, we did also run an uncalibrated version of the model with no data insertion. That model actually had the highest Nash-Sutcliffe efficiency. However, it failed to differentiate high versus average yielding years, and it didn't simulate the evapotranspiration as well as our other models, so we didn't pursue that any further. In conclusion, we've learned that assimilation of soil moisture observations can improve predictions of grassland productivity, and we're following this line of research even further. A couple things that we have going on to follow up this line of research. Number one, we have a collaborative review manuscript that's under development that's focused on using soil moisture information to better understand and predict wildfire danger. Secondly, we have a study that we are developing currently focused on addressing this question shown in the last bullet. Could soil moisture observations provide better guidance than the U.S. Drought Monitor, which is currently being used to target the $1 billion per year federal livestock forage program payments across the U.S.? That's a really important question, and I'll let you speculate about what the answer might be. Thank you for your attention, and I would welcome your feedback.
Thank you, and Tyson is in the chat as well, I believe. Do we have any open air questions we want to ask? Perhaps something everybody on the call would be interested in? I would ask, Tyson, do you have when you didn't include soil moisture insertion and you found a better efficiency, I'm wondering, have your thoughts evolved on that at all? Any ideas of, you couldn't differentiate, but I'm stumped by that.
Yeah. Well, It's a good question, Mike. It suggests to me that there's probably some potential to calibrate our model a little bit better than it has been. One of the challenges on these type of models, as Steve alluded to in his presentation or in his comments, I think in the chat maybe, is really the critical thing is the active rooting zone. But that sort of changes with time throughout the season, even in these perennial systems. And so that's not really well represented in our current version of the model. So that might be one thing that we could do that would improve what we have and make this, hopefully, as we try to scale this up and apply it to larger regions.
Okay. Yeah. More data, more diversity of data is useful.
Yeah.
Okay. Well, we'll move on to our next speaker. This is Mike Pilecki. As soon as I find the presentation. There we go. Mike Pilecki from CRN, recorded as well, and he's in the chat room. Ready to answer your questions.
Hi, this is Mike Pilecki from the National Centers for Environmental Information in Asheville, North Carolina, and going to talk to you about the U.S. Climate Reference Network operational changes in new soil moisture. The USCRN, of course, as you all know, has a set of soil moisture probes at about 114 of our stations across the United States. We conduct manual quality control of the soil moisture data here at NCEI, and we continue to improve our methodologies for automated quality control, as Ronnie Leeper outlined briefly earlier today. And we'll continue working on that during FY22. One of the biggest changes that's going on is almost completed. We have installed a new soil probe from Aclima at 46 of our stations across the United States, but they've been not being used for the layer average for soil moisture until now. At this point, we have gone ahead and finally finished quality control and analysis of the impacts that would have on our data, and we're confident that we can now incorporate the soil moisture data into the layer averages, and the recalculation process is about to begin shortly. It'll take place over about 2 weeks, and at the end of that process, the layer averages will be different for many of these stations from when Aclima was installed onward, and so we'll send out a notice to folks so that they will download the data again at these stations. Also, with regards to operations and maintenance issues, we are in the process of taking several of our research projects and taking them to operations, where we will be updating standardized soil moisture on a regular basis now, instead of having a static beta product out there. And also we'll be including a new product that's related to drought indices that's based on the standardized data set. So as I said, there are 46 stations currently that have Aclima probes installed, and there will be more in the near future, as we have now, well, it's not really post-pandemic, but we have gotten permission now for our colleagues at the Atmospheric Turbulence and Diffusion Division in Oak Ridge to start doing annual maintenance visits once again, after interruption approaching 18 months in length because of the COVID crisis. So where there are failed probes, they will be replaced with the CLIMA probes. We'll have a network that's a mixture of Hydra and Acclima probes for the foreseeable future. And so the analysis we did is important to show that we can go ahead and move forward with the data in its. Overall, we found that the Hydra and the Acclima soil moisture observation differences are very small. There are a few exceptions, a few cases where we have heavy clay soil, where the Acclima is definitely an improvement over the Hydra in terms of its quality of its measurements, and therefore has a more significant difference in those particular locations, of which there are a handful. It's not by any means a large portion of the network. One of the things that we can look at is to see how the seasonal cycle of the differences change between the time when we add the Acclima to the layer average, or just look at the pure Hydra layer average. And you can see that these numbers are very small, within plus or minus 0.01 of volumetric water content. And you can see that there is a seasonal tendency, though, that during the wetter season in the spring, the climas are slightly drier, and in the fall, when it's usually the soil is drier, the acclimas are slightly wetter than the hydras. Unfortunately, the temperature differences are much more substantial, which can reach 0.5 or 0.6 degrees Celsius at midday, and there's an overall high temperature bias of the Acclima over the Hydra. It's not exactly sure which one is more accurate as to whether the Hydra is perhaps suppressing diurnal cycle while the Acclima is accentuating it, but clearly there's going to be a discontinuity in the temperature records, which is unfortunate in this transition. As I mentioned earlier, we will be taking our standardized soil moisture product that's been around for a while and making it operational, where it's going to be updated in real time on an hourly basis. And we'll also be updating the soil moisture climatology product that goes along with that. That's on an annual update cycle, but is necessary to update both the climatology and the standardized anomalies when we update the climatology. So the entire set of standardized anomalies will also be updated. The newer product that hasn't seen too much visibility yet is Drought Indices product that's based on the standardized products, which will be a 7-day average of hourly soil volumetric water content, hourly standardized soil moisture anomalies, and also the percent counts of hours that are less than the 30th soil moisture percentile and greater than the 70th soil moisture percentile. This was recently published in June, and we're looking forward to having the community of US Drought Monitor authors use this to get an idea of direct drought indices based on the soil moisture data itself. You'll be able to find these as well as the other described data sets at our quality control data set link at the bottom of the page. The other research and development that has been going on as an offshoot of the Drought Indices project, we've developed a climatology of US Drought Monitor defined drought states for the NCLIME grid data set, i.e. 5-kilometer grid that covers the United States. And so you get a really a very acute spatial pattern of things like the number of drought events occurring during the first 20 years of the USDM, or the length of time spent in drought on the map on the right. We're also continuing our research in soil moisture standardization and applying it to the ESA, European Space Agency, CCI soil moisture data set. Chose that one because it's a bit longer than SMAP or other available single satellite data sets. It's a blend of multiple satellites, and the short-term interval period has lots of active satellites also, and the longer-term period is mainly dominated by the passive microwave data sets. So we're standardizing both in the same manner that we have also standardized our in situ data, with the idea being that we feel that using the same methodology for standardization in both will make them more compatible for blending purposes. That project is still ongoing. The other bigger project that just is beginning to start, but will be a dominant feature in next year, will be our examination of compound hazards of drought and heat waves, and using USCRN soil moisture to understand the interactions between the two and their. You can see here some of the preliminary results gathered by our summer interns during their work on the compound hazards project, and you can see that heat waves tend to be more intense, have a maximum heat index that's higher in the more humid areas of the country, in the Midwest and South and Southeast. You can also see in the lower right that when you compare heat waves during droughts to those occurring not during droughts, that the air temperature tends to be warmer. However, the heat index during the same comparison can vary depending on the local circumstances. And for instance, in the Southeast, it tends to be a lower heat index during a drought than a non-drought period, while in the Midwest, it tends to be higher. So we have upcoming in the next fiscal year, continued improvement of our quality control in real time. The Hydro Probe retrospective improvement project, which we're going to try to use different equations than the Loam equation to translate real dielectric to volumetric based on a new set of soil characteristics we've gotten in a recent study. And then finally, working more on this compound hazards project. So thank you for your time, and again, our web link and our quality control data set link. Thank you very much.
And thank you, Mike. You are in the chat, and as well, do we have any questions for Mike?
I think there was a question in the chat I can do verbally. The area of that's covered by our probes at a particular station would be about 3 to 4 meters by 3 to 4 meters. We have we're I think the only kind of national network that has 3 sets of probes at each level at each of our sites. So we do have this redundant measurement that also shows in the paper that I posted in the chat that basically even in that tiny area there is variation in the resulting soil moisture that you get within 3-4 meters of each other. So it's really an eye-opening kind of experience to see that there's that much variation in just a very small area.
Yeah, we had a study a few years ago that deployed networks around CRNs, and we could get out to about a kilometer. But if you go back to what Steve said, every station installed at a location with non-true TDRs really needs a soil calibration to be accurate. And then to be representative, you do need extra work to understand how that point measurement, because each of these measures really something the size of a soda can. To scale that out, you need to either collect more data or model out to larger scales. And the question is always, what is the accuracy to larger scale? And there's some maximum limit of any singular station for a sparse network like you have there. The triplicate is good, better than most, but the everything still needs a little bit extra work out in the field, right?
Yep, I would agree with that. It's definitely, that was another good study that we did there with you. Yep.
Didn't show the 3 profiles in our weighing lysimeter, but those are within a few centimeters of each other, and they're all 3 different. Even on a small scale, you need replication if you want a decent average.
Very good.
Other questions? Tyson,
I'll get to the chat ones after we're done here. So
yeah. Tyson,
just to join in on the discussion about replication, which is great, and I totally agree with, and just also to add that it's important to think about what we want the average to represent. So if we want the average to represent the station, then those don't need to be very far apart. As Steve just said, they can be centimeters apart and be giving you different data that you can average together. But if you want it to perhaps represent the field that the station is located in, then we probably need to take some care to get those replicated profiles quite a bit further apart.
Yes, I would agree. And we're just trying to characterize our stations as in the current time.
okay. There are a couple requests for some links for you, Mike, to post in the chat. The chat will be running all day, and will if you log out and log back in, sometimes you lose the prior information from your own window, just so you know. I'll have everything saved later, and we'll try and generate a useful links page with the things that are captured through the chat session here, and send that out to the attendees later, so that you don't have to worry about copying everything over as well, provided I remember to save the chat this time, which I've been guilty of not doing before. We are at the end of this session, and we do have an hour break, which is now less than an hour. But one thing we wanted to do is this is normally the traditionally time you would go out to your coffee session, right? Like, oh, coffee's in the back. We wanted to try and encourage that type of small discussion, and we're asking everybody to hang around for just 5 extra minutes, and I'm going to make random breakout rooms, and we will try and have everybody. I'm trying to see the number here. Very small breakout rooms of 5 or so people apiece, and just have a conversation. Introduce yourselves to each other. You don't have to go if you don't want to, but just to give everybody a chance to meet a few people one-on-one, instead of just reading their names in a list or hearing the few of us that talk too much on the live stream here. So I'm going to create these breakout rooms. If you feel comfortable, please go in and chat. Otherwise, we will meet back here at 3 p.m. Eastern Daylight Time for the next session on sensors and networks, part 2. And so you should see a window open up asking you to join a breakout session, and feel free to go and have a conversation. There's no reason to report back.